Hello and welcome. I am Navankur Ray, BE from Tyagaraja College of Engineering. Now we will see about back-to-back station. At first, let's take a quick look on what is back-to-back station. First question comes in our mind when we talk about back-to-back station is why it is used. The answer is, as we know that high voltage AC is used to transmit the electrical power for reducing the power losses and because of the flexibility of AC system. In a transmission system, different grids are interconnected, but sometimes it may happen that one or more grid or power system may not be in synchronization with other grid. To overcome these things, a HVDC back-to-back system is used. In an HVDC back-to-back system, two independent neighboring systems with different and incompatible electrical parameters like frequency, voltage, short circuit power level, etc. are connected via DC link. The basic principle of operation of an HVDC link system is based on the conversion of AC to DC and vice versa by means of rectifier and inverter, as you can see in the diagram. The process involved in this system is simple. Power from two or more neighboring systems is first converted into DC with the help of power rectifier system and summed up. After summing, the resulted power is again converted in AC with the help of power inverter and supplied to different grids. HVDC link has much more benefits. Some of the benefits are as follows. Power can be upgraded to desired frequency. Two asynchronous systems can be joined successfully without the loss of stability. Stability of the system is increased as well as power flow can be maintained within the optimum limit. More active power can be added where the AC system already is at limit of its short circuit capability. Now let's look at some real-time back-to-back HVDC station. Chandrapur back-to-back HVDC converter station is one of the station which is situated in India. The Chandrapur back-to-back HVDC station is a back-to-back HVDC connection between western and southern region in India, located close to the city of Chandrapur. It is the second commercial back-to-back station in India. The converter station consists of two independent poles, each with a nominal power transmission rating of 500 MW. Both poles were built by GEC Alstom between 1993 and 1997 and have a nominal DC and AC voltage of 205 kV and 400 kV respectively. Its main purpose is to export power from Chandrapur Super Thermal Power Station to Ramagundam of India National Power Grid. It is owned by Power Grid Corporation of India Limited. The project achieved load diversity of western and southern region in India grid by meeting high demand from surplus power available in the either region. Bidirectional power flow capability is also available in this back-to-back station. Now let's take a quick look on construction. It has two poles. Each of the two poles is identical and consists of a back-to-back connection of 12 plus pulse bridge converters. Usually no DC smoothing reactors are used. Each pole is grounded at one of the two DC terminals. Each of the two poles uses three single-phase 3-winding converter transformer on each side. The scheme comprises 48 thyristor valves, and with each thyristor valve including 54 thyristor levels in series. The thyristors are of 100 mm diameter and are rated at 5.2 kV. The thyristor valves are floor mounted, even though the station located in a seismically active area. Each side of the station is equipped with a total of 848 MVR. of AC harmonic filters. Each side of each pole is equipped with 306 MVR double damped filter and one 106 MVR C-type filter. On the southern side there are also two 50 MVR sun reactors. Now let's see the operation of Chandrapur back-to-back station. The converter station is located 20 km from the eastern terminal of Chandrapur phase HVDC transmission system. The close proximity of the two converter stations means that the control systems needed to be very carefully coordinated, a task made more challenging by the fact that the two stations were built by different manufacturers. To address this problem, a series of joint simulation studies involving the control equipment from the both converter stations connected to a common simulator was performed. On 31st December 2013, the northern, eastern and western grids were synchronized with the southern regional grid, creating a single synchronized AC grid over the whole of India. As a result, the converter station is no longer required for its original purpose of asynchronously linking the western and southern grids, although it can still be used as an embedded power flow device to help control power flow within the AC system. The station could potentially be shifted to elsewhere to export-import power from other countries. Sometimes the excess power fed to the southern grid by this HVDC link is flying back-to-back western region through the 765 kV AC lines between southern grid and the western grid with futility. Now let's see the McNeill HVDC back-to-back station. It is also one of the back-to-back station which is located in between Canada and Alberta. McNeill HVDC back-to-back station is a HVDC back-to-back station which interconnects the power grid of Canada provinces Alberta and Saskatchewan and went in service in 1989. McNeill HVDC back-to-back station is most northerly of a series of HVDC interconnectors between the unsynchronized eastern and western AC system of United States and Canada. The station was built by GEC Alstom and can transfer a maximum power of 150 MW at a DC voltage of 42 kV. The McNeill station was first HVDC installation to dispense with DC smoothing reactor, a component which most engineers consider as an absolute must at HVDC plant. Even today, only a small number of back-to-back HVDC stations have been built without DC reactors. The construction of McNeill back-to-back station. The 12 thyristor valves at each side are arranged in a conventional 12+ bridge. The valves are cooled by a mixture of deionized water and ethylene glycol, which does not freeze at a temperature of -50 degrees Celsius. These were the first thyristor valves ever to use water glycol mixture directly inside the valve, with no separate secondary cooling circuit. The valves use 100 mm 5.2 kV electrically triggered thyristors, with 11 in series per valve on the Alberta side and 12 in series per valve on Saskatchewan side. And now the operation of McNeill back-to-back station. The McNeill station was also notable for operating within an exceptionally low circuit ratio, the SCR. The SCR is a measure of how strong or weak the connected AC system is. Most HVDC schemes using line commuted converters operate with a SCR of at least 3, but the McNeill scheme was designed to operate with an effective short circuit ratio, ESCR. ESCR is a measure which subtracts the harmonic filters from the evaluation of SCR and is more meaningful on very weak AC system of less than 1. On the Saskatchewan side. This is one of the lowest ESCR valves ever achieved within a line commuted HVDC converter. McNeill was also first HVDC station to use three-phase 4-winding converter transformers. The transformers, which are connected to 138 kV on the Alberta side and 230 kV on the Saskatchewan side, and are each equipped with a 25 kV tertiary winding, in addition to the 2-valve winding. This arrangement allows the harmonic filters to be switched by vacuum switchgear, which is more tolerant of large number of operations than high voltage switchgear connected directly to the 138 kV or 230 kV busbar. This was the significant advantage since the extremely low short circuit ratio required to reactive power to be controlled within very tight limits, leading to frequent switching operation. Now let's look at the quick summary of what we had discussed till now. First we saw the HVDC back-to-back station. What is actually it is. So in an HVDC configuration, two independent neighboring systems with different and incompatible electrical parameters like frequency voltage are connected via DC link, as you can see in the picture. Then we saw Chandrapur back-to-back HVDC converter station, which interconnects Chandrapur super thermal power station to Ramagundam southern region of India national power grid. The converter station consists of two independent poles, each with a nominal power transmission rating of 500 MW. Both poles are built by GEC Alstom between 1993 and 1997 and have a nominal DC voltage and AC voltage of 205 kV and 400 kV respectively. It is the second commercial back-to-back station in India. Bidirectional power flow capability is also available in this back-to-back station. Then we saw McNeill HVDC back-to-back station, which interconnects the power grids of Canadian provinces Alberta and Saskatchewan and went in service in 1989. The station was built by GEC Alstom and can transfer a maximum power of 150 MW at a DC voltage of 42 kV. The McNeill station was the first HVDC installation to dispense with the DC smoothing reactor. The McNeill station was also notable for operating with an exceptionally low short-circuit ratio. And McNeill was also the first HVDC to use three-phase 4-winding converter transformer. The 12 thyristor valves at each side are arranged in a conventional 12-pulse bridge. The valves are cooled by a mixture of deionized water and ethylene glycol. So these are the references from which I have taken the concepts. Thank you.